Thank you so much. It's really an honor to be here, and really appreciate the invitation. And unfortunately, I was just able to come last night, but I watched some of the videos, and it's been really nice so far. And A+ pronunciation of my name, that was actually really impressive. Today I'm going to talk to you about some of my work in pricing and fairness and how we think about it in vehicle sharing systems. Before I go any further, this is really two papers. The first paper is with my former student, Xiao, and Maxime Cohen. And the second paper, which we just posted online, is with my PhD student, Yemi. And unfortunately, she couldn't make it to this workshop. Okay. So I just want to give a general background on specifically pricing, and then we'll talk about how it relates to transportation. So I started working on this 5 or so years ago, and as someone who works in pricing algorithms, my perspective has always been to sort of design algorithms that are simple for consumers. And that sort of led to thinking about fair for consumers. And it actually turns out under even under something like the Civil Rights Act and many other laws, it's just illegal to discriminate against protected attributes, of course. And that also translates to pricing decisions. Of course, as you all know, this is kind of hard to enforce because there's lots of features related to protected attributes.
Sorry, to clarify, what does attribute mean? What attributes here?
There's I think 17 official ones, like gender, sex, age, military status, marital status, things like that. Yeah.
So, and what does protected mean? What makes an attribute protected?
The government protects these discrimination against these attributes.
Okay. It doesn't mean the information is protected.
No, we're not talking about privacy here.
Thank you. Yeah. Okay.
Often the information is also protected or not available as well.
But the term here just means that's something that the government cares about.
Yes.
Giving special. Okay.
That's right.
Thank you. Thank you.
Yeah, I should. Yeah, be careful because a lot of things I'm saying is about the U.S. system. Just to give you some examples of what I'm talking about. So there's one thing called the pink tax, which you may have heard of, that shows basically there are certain products like beauty products and services where women pay higher prices essentially for the same thing. In New York City 2 years ago, there was actually a law passed that this is illegal. It's called the pink tax law. And actually, I know of a project right now where they're just going on Amazon and people are using ChatGPT to label products, and the pink tax obviously exists on a much wider spectrum than we think.
Who decides if they are the same thing or not?
So this is of course, there's no color assigned to genders or sex, but I guess the idea is the branding and where they put them in the stores and things like that. So sometimes they'll have a women's department. Sometimes they'll even say on the product for women. I'll actually show you an example.
It could be a more expensive product.
Exactly.
Sorry?
It could be a more expensive product, right?
Yes, exactly.
I'll show you. Yes, of course. Yeah. So, but the pink tax is referring to pretty much the same service. So another example is about people being charged different prices for a service such as test preparation. And probably the one that's I think about the most is about loans. So here the price is the interest rate on the loan. Okay, so you obviously want a lower price, lower interest rate when you get a loan. And there's a lot of research on this. And so there's some elements, back when there was lots of loan offers, there was lots of sexism and racism where people would get higher interest rates. But even as we move to algorithmic loans, where you just go on a website, enter something, there are still tendencies where minority groups tend to get higher interest rates. And there's even studies to show even if you condition on education and income, stuff like this, they're still getting higher interest rates. So this is not my expertise, but there's just giving you some examples that basically, despite laws, like these things still exist. And I like this quote. It says, like, it's important to consider the fairness of pricing in markets we regulate. It's also important to consider the harm that may be caused by particular types of pricing practice. However, fairness issues can often be more complicated, and the right course of action may be less clear. So that's like probably the biggest takeaway is like, indeed, I think this is not obvious what to do. It is complicated, and the consequences of fairness are not obvious, and sometimes opposite of what we want. So the research question is, how do we embed fairness into pricing algorithms? And how does it affect consumer surplus and social welfare? So I'll talk very briefly about the first paper, which is just kind of in a general, very simple setting, and then spend more time on the vehicle sharing context, where we're thinking about pricing in a vehicle sharing system. Okay, but they essentially use the same framework, and I think it's good to have a point of reference to compare these kind of two models. So here's like the simplest possible model we can come up with to think about fair pricing. So you just have a monopolist, and you're selling to two groups of people. Let's call them group 0, group 1. You can think about them as like Apple and Android users if you want. So we know the group has a certain population size, lambda I, and we're going to charge price pi to group I. And we're going to use the random utility maximization framework here. But it's pretty simple here. Just the idea is that each group has a valuation distribution. V, Fi is the valuation distribution. So we draw a random variable from there for the valuation. And so the market share from a group is the CDF at price pi. Okay, so that's the percentage of the market we capture when we price at pi. And please interrupt me with questions. This is a lot of people here, a new audience for me. So if I don't make sense, feel free to stop me. We're going to measure surplus using the classical economics definition, which is like your valuation minus the price, assuming you bought something. So if you didn't buy something, it's 0. If your valuation is greater than the price, you're willing to buy it, and the difference between your valuation and the price is your surplus. Okay, and the revenue the company gets is the market size times the price times the probability that someone bought. And so we have two notions of fairness we're going to consider. One is like what I've been talking about is price fairness. And just for fun, I put this example because some people were asking, like, it literally says his and her personal kit. It's the same exact kit. And they have different prices. So this is like a very clear example, but most of the time they're more subtle.
So why is this not allowed? I mean, every woman can buy the blue one, right?
So I don't want to get into that, but it's illegal. Now this is illegal.
Yeah.
That's all I'm going to say about that. Of course, yes, anyone can buy anything.
Okay.
Yeah. But like in fairness, though, like you're not going to think that someone is tricking you so obviously, right? So you're just going to like go and pick, oh, this is for me and take it, right? You'd have to spend a few minutes and be like, oh, wait, am I getting screwed? And it's like an unnatural thing to even ask yourself.
That makes sense, right.
Yeah.
It's kind of like taking advantage of identity too. Like, what if you identify as a woman and you're like, oh, I want to buy this thing that's supposed to be geared towards me, but it's like more expensive and you don't even like think about it. So like, yeah, that's kind of taking advantage of like what people believe about themselves, I guess, in some way.
Yeah, so regardless, this is straight up illegal in New York, at least. And then, of course, going back to the loan example, this is a lot more nuanced because it's done through algorithms. Yeah?
Do you have a theory to explain why Asians are doing so well on the mortgage market?
Sorry, what was your question?
Why Asians doing so well on the mortgage market?
Oh, we shouldn't read into this. This is just like one paper. So this is one particular data set. So I don't want to comment on that. I don't know. This is not my research. Yeah.
Because the banks trust them less.
More. Asians more.
No, they pay more.
But Asians less.
They should are doing the best.
No, they're doing the best. Yeah.
Okay.
They're taking over the world. Just a joke.
So let me move on to the other fairness measure consider. So it's not just price. So in the context of pricing, I think the most natural thing is to think about we want the prices to be similar. But there's actually a lot more other things you can think about. So one is the demand access should be similar. So we want, let's say, the demand values to be similar. What does that mean? Like the proportion of people in each group that can buy the product is the same or close to the same. So I think this is actually really interesting. So think about it like this is, so there's a picture of my campus here. What we do with like scholarships and fellowships, things like that, is kind of trying to ensure some kind of demand fairness. So if we just charge everyone the same price to go to college, it's going to really screw up our DEI goals. So we use pricing as a lever to help improve demand fairness. Okay? And so I think of tuition and fellowships, these are like pricing tools.
Using pricing as a metric of fairness is kind of complicated. Because basically in the US, I mean, there are basically cases in which the same products in a minority neighborhood versus the others have different prices. But also some of the shop owners argue, well, the demand is lower. I need to charge higher for the prices in order to break even. And basically there are other factors that kind of distort the picture.
Yeah, that's certainly true. So like it's sometimes you see like grocery stores in low-income neighborhoods that have higher prices on average for those kind of reasons. So like I said, this is a very stylized model, but there are lots of things that go into it that I'm not capturing. Like another good application is like I think in pharmaceuticals. Basically, if you live in the US, you're funding drugs for the rest of the world. So we pay much higher prices than other places. And that's somewhat of a good thing, so other countries can afford drugs.
Price discrimination.
Sorry?
Price discrimination.
Maybe we should keep some of the comments so we can go on with the talk.
Well, I thought I would speak on
Yeah.
So let's think about how to quantify this. What we're going to do is like think about fairness as on a spectrum. So we're going to measure fairness on a level between 0 and 1. So alpha is 0 means we're going to have no fairness. We're not going to impose any fairness on the system. And alpha equals 1, we're going to impose perfect fairness. So for price fairness, so we're just going to set the prices to be equal. And we kind of want to see what happens in between. So we're going to vary this alpha between 0 and 1. And here P0 star and P1 star are like the optimal prices when there's no constraints. So it's the unconstrained optimal solution. And so for demand fairness, instead of prices, we're putting the market share as the constraint. And what we're going to do is we're going to try to measure the total profit. So the company is trying to maximize their profit, which is the sum of, again, lambda times the price times the demand for each group. We were going to measure the surplus, the combined surplus and individual surplus, and the social welfare is the profit plus consumer surplus. Okay, so the regulator is kind of thinking about social welfare. The company is thinking about their revenue. And so if you look at the classic economics like 101, what you would know is that the welfare with 0 fairness constraint is higher than perfect fairness. So it's actually better for social welfare if we're allowed to charge different prices to different groups. Okay, versus one price. But really nothing is known in between. So if we put some constraints on that, what happens? And it turns out you can even do better than no fairness. So that's what we're going to show. So here's like the first result. So let's just say the simplest model again, what I described with a linear demand. And this is what happens as we increase the fairness from 0 to 1. So 0 again is no fairness, and these are the optimal prices. And we're keeping track of the revenue, the welfare, profit, and surplus. Okay. And what you can see is as I increase the fairness a little bit, the social welfare goes up a little bit, and the customer surplus goes up. Okay, so this is benefiting people, benefiting society overall. Of course, revenue or profit always goes down because I'm imposing a constraint on the company. And what's happening is that the price of the lower price is going up, the higher price is going down. So for group 1, I'm reducing the price. Group 0, I'm increasing the price. Up until a certain point, and then something weird happens. As you can see this weird discontinuity. What's happening is that at some point, I'm imposing such a tough fairness constraint on the company that the company says, screw it, I'm just gonna not even bother with group 0, and I'm gonna focus on group 1. It's not even worth it. So what they do is they charge the optimal group 1 price to both groups, and that's actually more profitable. And basically group 0 is getting completely shut out of the market. Okay? And if you think about it, like companies do this, right? They'll focus on like high-end customer segments sometimes. So this is already start thinking like, okay, like, is this really what we wanted with price fairness? A little bit unintuitive, right? So just increasing alpha to 1 is not necessarily a good idea because you just end up shutting people out of the market. But increasing it a little bit does seem pretty good in the sense that it's increasing the social welfare.
Sorry, on the technical thing, I haven't fully understood. Why would you raise the other group price to the same level?
Because it meets the fairness constraint.
Because of the constraint, but
yes.
It means nobody buys in this
Yes,
setup,
it's
right?
basically like above their maximum willingness to pay.
Okay, yeah.
And satisfies the constraint at the
In
same time.
reality, you would assume there's a distribution, right? That there's still like a marginal number.
Yeah, so this is, because it's linear demand, that's why you see like this discontinuity. The same, if I show you I didn't put it because I want to get to the vehicle sharing, but for like other demand models, it's not a discontinuity, but it's a very sharp, because it ends up being like a bimodal distribution and just get rid of one of the modes. Yeah. Good. So, and the theory set, we can prove basically this exactly happens and characterize everything exactly. So that's the theory in words. Now, what happens if we do demand fairness? Okay, so something interesting happens that as we impose more and more demand fairness, everything gets worse. So the profit goes down, of course. The social welfare also goes down. And customer surplus goes down overall. But one good thing happens is that for the lower valuation group, their surplus goes up. And that's like exactly what you would kind of want to happen. So as we give more favorable discounts to like low-income groups, that actually benefits them. Okay, so we're trying to improve the access to both groups.
Demand fairness means you make sure that each group gets the same amount of the product.
Yes. Fraction. Of course, normalized.
Fraction, yeah.
Yes. Yeah.
Proportion of the group
Yeah.
that receives the good is the same for both groups.
So that's the sort of two punchlines from the first paper, and then move on to the next part. Seeing if there's the clock. Great. So this was like an unconstrained monopolist, and I'm a operations research person, so it's kind of interesting thing about it. Let's think about it in like a real system. And so we thought about let's think about a vehicle sharing system. So I use these things every single day, whether it's a bike or a car. And there's this nice paper from a few years ago that shows that in Chicago, if you look at the prices for Uber, I believe, they can show that on average, younger, more college-educated, poorer, and more non-white people pay higher prices. Okay, not causation or correlation. Nothing about causation here. This is just like the data on average and what it's saying.
What is your explanation, if I may ask?
So, well, we're going to get into, that's kind of like a lot of what we're going to talk about, but when I showed this to like Uber people, they immediately like don't want to look at it. And they're like, oh, well, they're not thinking about the resource issues. So the big difference here is that there's a finite number of vehicles. And these vehicles, you cannot get a ride unless there's a vehicle. And so the prices are not just controlling what customers want to do in terms of affordability, but it's also controlling where the vehicles are. Okay, so part of it, so these apps are not using the demographic information to do pricing. I'm pretty sure that's not the case. But they are using location, and location is correlated to attributes. So nevertheless, this was more like a motivation for like, let's study this kind of system for fairness, and what does it even mean? And then there's some, so this is about price fairness, and then about access fairness, there's some nice literature showing that for bike and scooter, these are I think mainly papers in Europe showing that bike and scooter sharing systems, accessibility varies a lot with the protected attributes as well. And so here's some of our own analysis. And I'll get back to this case study at the end. But this is just a preview. So we took data from New York City, open data initiatives, and we computed for just like a particular 2-hour window last year, on one particular day, what the average price and access was in New York City. Okay, and the short story is, you can see there's a lot of heterogeneity, whether it's price fairness or access fairness, and you can see that they're very different colored. So that's what we're going to talk about next, yeah. Access is the product of, can I afford the service, and is there a vehicle available to give me that service? So we're going to model that explicitly. Okay, so that's the motivation. So again, we're going to ask pretty much the same questions. What is the right criteria for fairness in a vehicle sharing system? And this is all, by the way, from the consumer perspective. And so there's a lot of work actually from the driver perspective, which is very important and interesting as well. But here we're just thinking about consumers. And like in bikes and scooters, there's no drivers, of course.
Sorry, I should have raised my hand when the previous graph was up.
Yeah, please.
I presume you can't do this, but if suppose I did price per second instead of price per mile.
Yeah. Mm-hmm. Yeah.
Or there's economies of scale.
The fare is per mile.
The fare is per mile.
There is actually
Yes.
mile and time. It's both, the rate card has both time and
So what we do explicitly is like we get the base price and the price per mile and all the actual amount of pricing stuff, not the tax and tips, and then we divide that by the mileage. But yeah, we haven't actually looked at the price per time.
because as I look
We
at
haven't
that
looked at
map, I tell you, I also know the rate of traffic in each of those regions.
And the other
Is rather different, and,
the other
and
thing is-
so the map would look. I'm suspicious that the map would look very different on a time normalized.
and the other argument could
I
be
have
that
interviewed your drivers, and what they explained to me is a combination of distance.
Yeah, I know.
Exactly.
Yes.
I create
Yes,
those,
it
those
is,
rate cards. So,
Okay, and basically, and it's a combination of distance.
right, but in terms of, again, if to get a question of thinking about, I mean, from a customer point of view, you care about, in some sense, per mile, because that's what
What you
you're
get.
you're achieving. But again, as you sort of think about it from a driver point of view.
Yes, yeah. No, so I think you're right. And one of the things we're not going to model is time, because it makes it complicated.
I
yeah.
agree that the data is
Yeah.
is.
But for the case study, we could possibly do it. So that's a good point. Yeah. And by the way, we just posted this, so like the feedback is very welcome and encouraged. Yeah.
So one more feedback is there might be differences in the length of the trip that people are booking, and if you get a longer trip, it's more worthwhile to take it, so you offer a lower price. I don't know how the algorithm works, but if I want to go for 20 miles, I'm getting per kilometer price lower than if I go for 3 miles. I would
That's right.
assume.
And that is sort of, yes, that is true. And that's why there's a base fee to get in the car, and then there's like per mile and per minute fees. Yeah. That is true. Okay, good. So we're going to formally define what is fairness here from the consumer side, and what is the impact of imposing some fairness criteria. All right. So here's like what we're going to do. We're going to again create the simplest possible model, and then see what happens. So we're going to have 4 parts here, so that we have to think about the customers, the vehicles, the platform, and the policymaker. Okay. So the simplest thing you could do is have 2 locations. Okay, so people going from 1 to 2 or 2 to 1. And when we talk about fairness, we're thinking about here fairness of people who live in the 2 locations. Okay, and actually we can handle more than 1 vehicle, but if you want, just imagine 1 vehicle. And so at each location, we have a different market size, lambda I. Again, trying to use the same notation from before, and this is a Poisson process. And again, we're going to have a valuation distribution or willing to pay distribution. And for example, if it's linear demand, that corresponds to a uniform valuation distribution. So we're going to look at specifically linear and exponential demands. And so if you set a price, PI, P1, let's say to go from 1 to 2, the total traveling rate is capital lambda times the CCDF at PI. Okay? So this is market size times the sort of affordability. And we're going to assume that vehicles here are not relocating themselves and traveling time is negligible. Of course, these are big assumptions. So what is the platform trying to do? Again, they're going to try to maximize revenue by setting the prices. So here we have two kinds of constraints. There's the balance constraints and the fairness constraints. So the balance constraints, for those who don't know, it's just trying to say what fraction of the time is the vehicle spending at each location, if there's one vehicle. If there's more than one vehicle, it's telling you what fraction of time, how many vehicles there are at each location at any point in time on average. Okay, so this is kind of like a steady state way of thinking. And it depends on the arrival rates you set. So these lambdas depend on the prices. And so again, we're trying to maximize the revenue subject to these balance constraints. And we're also going to have the fairness constraint. So what is the fairness constraint going to be? So again, we're going to think about two kinds of constraints. One is price fairness, and the other is access fairness. And so someone asked before, what is access? Here we can formally define it now. So access is the probability you can afford the product times the probability that the vehicle is actually there. So if there's no vehicle there, even if I want to buy it, I'm not getting access. And so as you know, I don't have to pitch to people here, like access is kind of a fundamental aspect of transportation system. Any questions about this?
I don't know this for sure, but I've heard that there was some ride shares where the drivers could choose to accept the trip or not, and there was something that drivers refused to go to certain neighborhoods purposefully. So the driver's psychology played a role in this as well. A,
yes.
Is that true? And B, would that affect the modeling here when you talk about availability of a car?
Definitely true that drivers can reject requests.
Yeah.
I think in recent years they've played a lot with the information the driver receives so that they're not discriminating in particular.
The driver knows which neighborhood to go to, right? So based on the address.
Right. But they actually, like, I think you used to get like names and pictures, and now they kind of try to avoid that.
It helps a little, but of course the driver knows the city, right?
No, the driver knows where they're going. I think if it's over a certain range, they know like a lot more information because they give the driver more information.
I see.
But anyway, the point is they have
going
information.
to. I mean, of course, they have to know where the pickup is.
Yes.
But the question is, at what point does it get revealed where the other end destination?
I think if it's short, they don't know too much, but if it's long, they do know where it's going.
Okay.
But the other part of your question was...
What's more important? What does availability of vehicle mean, right? If the driver could decide to reject a trip based on racism,
Yeah.
for example.
So I would say, I think this paper makes a lot more sense for like bikes and scooters because I think the driver part is important. The interesting thing is that like bikes and scooters are like, the pricing is uniform. So like the data is less interesting. So actually, like one takeaway is like, actually, I think we should be pricing the bikes and scooters using some kind of not uniform pricing to achieve some of these fairness constraints. David is nodding, so that's good. So oops, it's okay. Yeah, so that's the short answer. Yeah, you had a question, David.
But I guess, part of it is you're assuming independence of those probabilities, right?
Yes.
And I'm a little worried about that, even in the bike setting.
I have a comment. I don't know.
Wait, don't you let the speaker respond?
I suppose that
No, but he asked the question. I didn't respond yet. So you're worried about these being independent.
You are assuming they're independent, right?
So what I'm willing, yeah. So I'm assuming they are independent. But if I'm thinking about it, if I know there's like less cars around, then I'm probably willing to pay more. Indeed. So yeah, maybe, of course, they're not fully independent. We're like, yeah.
I don't know much about this particular thing here, but I know a great deal in the case of similar problems in freight. In essence, the carriers have a preference to go back to the basis. And if you have multiple time periods, I mean, the preference is to go to deliver a load in locations in which they get another load, and that affects the pricing. And the question to you, have you noticed, because in this case, it's a multi-period game, that basically at 7 o'clock in the morning, there is a demand going in a given direction, and then that may change prices because of the possibility of getting like a paid customers going in the direction they want.
Yeah, so I think definitely like the drivers are strategic and they choose their whole schedule and where they work intentionally. In some sense, the pricing mechanism are trying to like reduce that to the best they can, but there's always going to be some opportunities probably. So yeah, we don't model a lot of that, and even like the way we're gonna think about this model is something you would, in terms of like the dynamics. Of course, the commuting patterns are changing hourly, so it's more something you would redo every hour or two. But we don't have any kind of dynamic model or anything like that. So the main contributions here are theoretical, and I'll get to that in a second. And like I said, I think it might help to just think about the scooter and bike sharing aspects, because indeed, like the driver incentives are interesting, but we don't model that. So let me tell you one thing. So like if you work in the world of fairness, you have to have an impossibility result. That's just like a fact, right? So here's the impossibility result. Basically, it says you cannot achieve perfect and access fairness at the same time unless you have very trivial instances of the problem, which are not realistic. So I'm just going to skip that. But the idea is like we should really just think about trying to optimize one and not both at the same time. And which one you want really depends on the kind of system you're running. Maybe it depends if it's a government system or for-profit system or things like that. So what is the optimization problem we're solving? Again, we're going to maximize revenue subject to the fairness constraints, and we're going to think about the price fairness and access fairness. And again, we're going to think about varying alpha from 0 to 1. So 0 means no fairness, and alpha equals 1 means perfect fairness. And again, we're going to measure consumer surplus and social welfare. Now the surplus is different because it's not just valuation minus price, but also the availability matters. So just because I'm willing to buy doesn't mean I actually get the service. I only get the service if the car is available or the bike is available. And the welfare is the revenue plus surplus. Okay, so here's like the first result. So this is the analogy to the unconstrained monopolist setting, the same kind of situation. What happens when we impose price fairness? And this is for linear demand. So basically what happens is that there's 4 possible things that can happen. So the picture is a lot more complicated now. And we've color-coded the 4 regimes. The theory says like one of these 4 things must happen, and we characterize it exactly. So the picture really is the theorem. And in 2 of the regimes, welfare goes up. In 2 of the regimes, welfare goes down. Okay, so price fairness can hurt overall social welfare, even a little bit of price fairness, unlike the first paper I showed you. What's interesting is that there is a setting where both sides of the city, node 1 and node 2, both of them benefit. So the surplus can go up at both locations, and the welfare can go up overall, which cannot happen in the unconstrained monopolist setting. So why is there a situation where everyone can benefit? Let me show you. Yes.
You can exchange lambda 1 and lambda 2, right? So there should be a symmetry of going from lambda 1 over lambda 2 to its inverse.
Yes. So
it doesn't look somehow symmetric with respect to
it's because it's like a ratio. So like.
Yeah, but I mean, if one is bigger than the other, you can switch lambda 1, lambda 2, and then the other is bigger than the first, right? So
yes. So it goes from 0 to 1 here. So it's kind of like this inverse thing gets captured here, but it's not exactly a mirror image because it's a ratio.
No, I said that there still doesn't seem to be a symmetry. Like there should be the analog of the blue region under the symmetry map, and it doesn't seem. Am I wrong?
So they're not entirely exchangeable because we're assuming that V2 is bigger than V1 on average. So I'm not showing you 0 to 1 here. So I'm assuming that, we're looking at only the region where V2 is bigger than V1. But yes, of course, there's like some symmetry that can happen. Yeah. That's the question I've asked my student when she first showed me it, and indeed there was something wrong. so for sure, yeah. And then we actually that question led to like this theorem kind of working out so nicely. So we can characterize all this. So how can both sides of the city benefit? So what happens is so node 2, which has the higher price, because we're imposing price fairness, we're going to force the price to come down. And node 1, we basically keep the price the same. And so node 2 benefits because we're reducing the price. Why does node 1 benefit if we're just keeping the price the same? Because there's more availability. So we're getting more people to take the trip to node 1, and that gives them more availability, so they're happy with that too. So that's how we can benefit both sides. Of course, that's one regime. So the regimes are dependent on the ratio of the market sizes and the ratio of the expected willingness to pay. Okay? And you can have regimes where the welfare goes down, which we didn't observe in the first paper as well. So the situation is a lot more complicated when you model the operations. And again, lots of things we're not modeling, but that's what we show. And for exponential demand, it turns out there's only 2 regimes. So there's one regime where everyone is better off, and there's another regime where everyone is worse off, actually. So even the demand model makes a big difference.
Adam,
Yes.
can you just say really what you mean by exponential demand, just for what the 2 distributions are?
The exponential distribution.
For each of them with
different rates. Yeah. And linear demand is uniform distribution.
Oh, with different upper bounds.
With different uniform distribution. Yes. And so what happens with access fairness? So this is kind of my favorite result, even though it's probably the most obvious result in hindsight. So the surplus at both locations and social welfare decreases. Everything gets worse. Everyone is worse off as you impose access fairness. So again, like it's kind of, if you're designing a transportation system, you want people to have access, and you want it to be, if you think about trying to make the access equal at both places, this turns out to be worse for everyone. So what happens is basically to get the access to be the same, you end up increasing prices at both locations. And at the extreme end, the perfect access fairness means that nobody rides. So it's like if you have kids and they're fighting over a toy, what's fair is nobody plays with the toy. And that's what's happening here. So theoretically, the way you get perfect access fairness, the only way to do it is that nobody rides. Like I said, kind of obvious in hindsight, but when we saw it, it's still surprising to look at it. And again, this is different than the unconstrained setting, so.
Who does it first?
No such thing. In the unconstrained setting, again, this is different because one group does benefit. The lower valuation group does benefit.
But also that is given that you're not considering the utility.
Sorry, I missed your question.
You're only using as a measure the prices to see what there is. Okay, the traveling has a utility. And basically, if you don't travel, I mean, you lose. Yeah.
So we're modeling, so here the objective is the platform trying to maximize their revenue, subject to fairness constraints. So basically, if you tell the platform you have to have equal access at both locations, the platform's just going to shut down. It's not possible to achieve it. Unless you have like, everything is the same between the 2 cities, of course. Then you could do it.
But it's linked to your basic assumption that there's no rebalancing of the vehicles, right? If you would loosen that, then it would change the story.
Right. So that's why you do see a lot of rebalancing, and that's something David has worked on a lot. For bike sharing systems and things like that, because you do need to balance them. And by the way, so this is the 2-node model. if we have time, a few more minutes, I'll tell you briefly about when you have more nodes. And then everything doesn't shut down, but what happens is some routes get shut down. So some edges get shut down, but not the whole system gets shut down.
And I was going to ask at the end, but given where we are now, I'm going to just interject. It seems like it makes sense to sort of think about a two-period model, because you can sort of imagine that if you just think of the two nodes, some fraction of the population in one sense is, as you sort of think, is some blend of residential and commercial. And as you think about what's really happening, I'm thinking the bike sharing domain, the ability to deliver in the opposite direction is a function of something happening in the previous period, in the first period. Because you only have, there's rebalancing, but rebalancing it can only do things at the margins. Whereas if you need a functioning system, you need sort of the balance of flows overall. And to me, it seems like here, access fairness might be the driver to actually having net profit for the platform. You sort of think about how I do price differentiation to compensate for the relative imbalance between the pressures of the demand in the two different directions, which flip from one rush hour to the other rush hour,
Right.
if you will. And so I just, to me, it seems like you might be in exactly the right place to do the next interesting step in a theoretical setting, which shows that actually access fairness is precisely what you need for the for the profit maximization of the platform.
Yeah, so I think what you're touching on is like that the access fairness and the balance constraints are very much tied together, and somehow there should be some
in a
way.
sort of magnet flipping kind of way, where that in order for success, profit of the platform overall, you need actual sort of two-period effect, because that's really what's the driver the sort of ability to think about indefinitely of availability in one direction is a myth. These are vehicles, whichever kind they are, that have to go back and forth.
Yeah, that's I think that could be a pretty good way to extend it. Thank you. So let's see. So in 5 minutes, I just want to say, so the problem in terms of like proving nice theorems gets pretty hard. So we don't do that when we extend to an arbitrary graph network. But we are interested in solving the problem computationally, so we can do like a case study. And this is also really hard. So like optimizing a closed queuing network in general is very, very hard, because there's lots of states and things like that. So and we have to also change the definitions of what does fairness mean. So like you can think about fairness across all pairs I and j, or you can sort of average at the origin. So those are what we call trip-based and origin-based fairness. But one sort of nice thing we can show is that there's a sort of nice series of papers in the operations research literature about pricing algorithms in these sort of what we call reusable resources or ride-sharing systems. And basically the short story is if you add access fairness to this framework, you get all those theorems to pass through, which is really cool. The price fairness doesn't work at all. So the price fairness constraints are really hard, and we just basically use like heuristics and global solvers to work to do those. So I'm telling you that because I want to show you a little bit about the case study. So the case study is like in Manhattan. Again, lots of assumptions. But what we did is we split it up, Manhattan, into 10 zones. And we're just looking at like one time window in one particular day. And we have the data from all the taxis and ride-sharing systems all provide their data in this database. And we're going to sort of take the lens of just one of the systems. We'll just take the lens of Uber. Okay, so we're Uber and we're trying to maximize our profit here. Okay, so we estimate the number of trips easily from this data set. And we can get like things like average weighted price from the same origin and things like that. And this is what I showed you before. So a little bit about more about the parameter estimation. How do we estimate the number of vehicles? That's kind of tricky, but we kind of look at the number of trips divided by the number of service time, divided by the average service time, things like that. And we actually have all this code online, so you can definitely play with these assumptions and see what happens if you're curious. The hardest part of this case study is estimating the demand function. So as someone who works in pricing a lot, this is kind of a frustrating thing in my field. There's very little publicly available data sets to estimate demand models. And the reason for that is it's very sensitive data. Like no company really wants to give that away for free. Only bad things can probably happen if that's publicly available. In particular, the data set we have only shows the accepted rides. So we don't know who did not accept rides. So it's really hard to estimate demand function when you don't know that all the people who rejected the ride, which is probably way more than the ones who did. So here's the trick we did. It's very simple. So we know that the valuation must be greater than the price for someone to accept the ride. So basically, the price distribution is kind of a lower bound on the valuation distribution in some sense. So we're kind of just using the price distribution as a hacky way to estimate the valuation distribution. And that's what the price distribution looks like for one of the edges. This is just one particular edge. But for most edges, it looks something like this. And like pretty remarkably, the logistic function fits this really well. And that's the most standard pricing tool in practice. So that's what we use. And so here's what the results look like. So if I force price fairness on the platform, what happens? So of course, revenue goes down. And the regime we end up in, out of the 4 regimes, is the one where actually welfare goes down a little bit too, and surplus on average. And if you want to improve the fairness by 10%, it would only cost the platform like 1% in revenue. So that's pretty nice. So a little bit of price fairness. 10% increase price fairness only requires like a small loss in revenue, and perhaps like that can be offset in some way. And this is what it looks like by neighborhood in terms of the surplus changes. Okay, so some places are better off and some places are worse off, which is something you should expect. And again, this is just one particular time window at night. So probably in the morning, like these pictures are flipped. Yeah.
But this exactly, the conclusion you just drew weighs heavily on the independence of the access fairness and the access probability and the price. And that's assuming that
which conclusion?
The
loss in revenue?
Yeah. That if I change the pricing mechanism, that definitely affects the availability because drivers respond to the price heat map.
Yes. So this is.
So
sure,
I mean, I'm just.
But these are relatively small changes. So like a driver would not really pick up on these so much, but you have for sure you have a point.
Sort of how subtle drivers are.
Yeah, for sure. So yeah, for sure. Like we're not here. The vehicles only move because the passenger requests. Yeah.
This is with the true number of cars, or is this in the m equals infinity limit?
No, this is the number of cars is like several thousand. So we actually looked at the number. We tried to estimate the number of cars too. With the data, yeah. It's several thousand. So solving these is really hard, actually, computationally. And just, I'm out of time, but just to show you for access fairness, something pretty cool happens. So basically, there's very, very little loss in profit to achieve access fairness. So like to increase access fairness by 50%, for origin-based access fairness at least, requires like a minimal loss in revenue. And this is how the picture changes again. But I should just wrap up. So just the takeaways are that I think the biggest takeaway is like fairness can have very unintended consequences and non-obvious consequences. So this is like a first study from the consumer side. Of course, people mentioned like 5 different directions already to take this in. I think access fairness can result in a lose-lose situation for everyone. But practically, in the case study, it turns out, although everyone is going down a little bit, it's very little. So that's kind of interesting. So the magnitude turns out to be not that much, although it does hurt everyone. And price fairness can actually help everyone, depending on the regime you're in. And I think I'll just stop there since I'm out of time. Thank you so much.